Okay, so I just posted the prep guide and the formula sheet to Blackboard, so you can enjoy those. Prep for the big opportunity coming up on Tuesday. Let's continue talking about radiation transfer and all that sort of thing. So we had written down the equation of transfer. As we'll see, this is, we're later going to add what happens if you could have photons being added to the beam as well as being removed, but just as a reminder, all we're talking about is absorption, which to astronomers is true absorption and scattering. D lambda is minus kappa lambda rho I lambda d pass. And then we had been talking about this idea that if I have a 1 meter by 1 meter area, and I imagine that there's a particle coming in, and we consider all the atoms, shall we say, that are within a cubic meter, in other words, 1 meter path length through 1 square meter of area. There's all the atoms that are within that cubic meter, and each one of them has cross-sectional area sigma. We're treating them as little hard spheres, such as the photon hits the particle, hits the sphere, it's absorbed, and if it misses it, then it is not absorbed. We argue that the probability that here we're talking about photons here. Probability that a photon interacts with any one atom. Now later we'll see, well, those could be electrons or something else. Electrons are little point particles, we think, but we can still talk about an interacting cross-section. Anyway, probability a photon interacts with any one atom within the 1 cubic meter volume that we're talking about is the percentage of 1 square meter covered by an atom. I remember we were talking about that. So in other words, if I just shoot a particle in at random and it's going to pass through this square meter and through 1 meter of path length, so there's this cubic meter, here's all these atoms in there. For any given atom, the chance that the photon will interact with it is the fraction of 1 square meter that that atom's cross-sectional area covers. So in other words, it's going to be sigma over 1 square meter. That'll be that probability. It's really the reason why sigma has units of area. Sigma is an area, it's in square meters, and so probability, what's the units of probability? Does probability have units? No, it doesn't, so it has to be dimensionless. So that's the idea, that's the basic idea of why we talk about interaction cross-sections, and last time we argued that kappa lambda rho is the number of square meters of cross-section per cubic meter volume in along the path that the photons are traveling. So that's supposed to be a reminder of what we did last time. Maybe you forgot something. Maybe you're not clear on something. What questions do you have? Including, I have no idea what you're talking about. Remember, that's always a good thing to say too. If you're like, what the heck are you talking about, Dr. Warner? Okay. And so then, let me find it in my notes here because it's not in the same order here. Yeah. So the way that we can define sigma in general definition of the interaction cross-section. That's going to be sigma, triple equals 4 defined by equals number of interactions. I'll keep it general. It could be scatterings, it could be absorptions. Number of interactions per target particle, I'll call it. Atoms, electrons, etc. So these are the things that the photons might interact with. So I'll just call target particle. Number of interactions per target particle per second divided by the number of incident photons per square meter per second. And this will be proportional to the incident flux. Right, the energy per second per square meter in those photons traveling along the beam. Because the number of photons, if they all had the same wavelength, the number of photons per second per square meter times the energy of each photon would be the flux, would be the energy per second per square meter. And the reason it has this definition is this argument that we were making here. In other words, if I had one particle pass through this square meter, through 1 meter, if I just had one particle pass through this square meter, and I consider one target particle, again, the probability that that particle will interact with that target is sigma over 1 square meter. Sigma is that sigma over 1 square meter. And so, how do I want to say this? So this is kind of a per particle thing. And if I have 2 photons passing through there, right, then the probability that a photon, one or the other, will interact with the particle is now twice as large as it was before. Two photons that can interact, where you double the probability that one of them is going to interact with one of those atoms, and so on and so forth. And so, in other words, we have to divide by the number of, so if we get the number of interactions per target particle per second, that will be proportional to number of photons coming in which is why we have to divide by the number of incident photons coming in per second. If twice as many photons were coming in, you'd get twice as many interactions. 3 times as many photons coming in, you get 3 times as many interactions. What is the units of sigma? If you just look at this, what are the units of sigma? It's meters squared. Units are meters squared, right? Because the second units cancel out. particles isn't a unit, right? It's just a number, it's a pure number. Number of interactions, number of photons, those are just numbers. So the units of this is in fact square meters. This ratio will have units of square meters. So even if you have a general notion of target particles that aren't little hard spheres, you could do an experiment. You could send in some number of photons per square meter per second, and you could imagine there's an atom sitting there, and you send in a beam of particles with some number of, a beam of, this works for any kind of particles, but here we're using photons. Send in a beam of photons, and you know how many photons per second per square meter are in the beam. There's your target particle, and you do it with many, many target particles and account for that, but whatever. There's your target particle. You can measure, in principle, how many interactions per second for that target particle divided by the flux. You could make that measurement, and you would call that the collision cross-section. So in other words, this is general. You don't have to have hard spheres. It could be just an electron sitting there, which has no literal area whatsoever. But you could still figure out what that is equal to and call that the cross-section for interaction of the electron, or whatever kind of particle it is. So in other words, in general, are atoms little hard spheres? No, they're quantum fuzzballs, but you can still talk about the collision cross-section because you could construct that ratio right there. You could either do an experiment to figure out what it is, or you could do a fancy quantum calculation to figure out what it should be. And so this is more general than just literal hard spheres where they have a definite cross-sectional area that we're talking about. What questions do you have? So give this some thought. It's worth thinking carefully about and understanding exactly what's going on here and why it works out like that. Okay. Let's see. Can I erase this stuff? The stuff on this board. You got that down? It's gonna go. It's gonna go. All right, so let's start working with this. For a light beam, you've got a bunch of photons all moving in the same direction. For a light beam, with I sub lambda, specific intensity per unit wavelength interval equals, let's say, I lambda naught, some initial value at s equals 0. And remember, s marks distance along the beam, distance along the direction of travel of the photons. We have 2, 4, 6, 8. It's now time to integrate. We'll integrate both sides. So first of all, bring I lambda to the other side. We got pi lambda over I lambda is equal to minus kappa lambda rho ds. So now we've separated it. Integrate both sides. The left side with respect to I lambda, the right side with respect to s. I lambda naught to I lambda of di lambda prime over I lambda prime is equal to the integral minus the integral from 0 to s of kappa lambda rho ds. Right, so in other words, here's my beam. Here is s increasing in that direction. here is s is equal to 0, and here I am over here somewhere, and I lambda is equal to I lambda naught, some initial specific intensity here, and it's equal to I lambda at some particular value s, and we want to know what that is. Will I lambda be more or less than I lambda naught in this scenario that I've drawn here? Here's I lambda naught. Is I lambda over here going to be more or less than I lambda naught?
More.
It's going to be more. But wait a minute. Aren't photons being absorbed and scattered out of the beam in between here and there? So I ask again, will I lambda be more or less than I lambda naught? Less. Yeah, later we'll talk about where you can also have emission along the beam, and it might actually get brighter because there's more emission than absorption along the beam. But if there's nothing but absorption and scattering, I lambda is diminishing as you move along. That's what the minus sign, remember, was there for. We're losing photons from the beam. And we're doing two definite integrals with respect to two different variables, right? And so the limits have to correspond to one another. I lambda is equal to I lambda naught at s equal to 0, and we're saying it's equal to I lambda at s equals s. I'm going to be a good mathematical citizen and say that I'm integrating with respect to I lambda prime over here, and that should be I lambda, I'm calling it 2, I lambda prime, and to s prime, because Dr. Nunemacher would be mad at us if we called the limits of the integration the same thing as the integration variable. We don't want, or any other mathematician, to be mad at us, so we changed the name of our variable of integration. Physicists are bad about that. Physicists will often say the integral from 0 to s of kappa lambda rho ds, but that's, no, you should use a dummy variable, right? You shouldn't call the limit the same thing as your integration variable. Okay. What's the integral of di lambda prime over I lambda prime? What's that integral? What's this indefinite integral? The integral of dx over x integrates to what? Yeah, natural log of x, right? So over here we've got, this is natural log of x plus constant, but if I'm doing a definite integral, the constant's going to go away anyway. So this will be the natural logarithm of I lambda, the natural logarithm of I lambda prime, and we're going to evaluate between I lambda naught and I lambda. And what about this one? What does that integrate to? What's the, well, so here, if I could assume kappa lambda and rho were constant, or at least, this would be, they have to work out this way, kappa lambda rho were constant, I can pull this out of the integral and just call this minus kappa lambda rho s, but I'm not going to make that assumption. I'm going to assume that kappa lambda and rho are functions of position, and so since I'm not specifying what they are, I have to just leave this as this integral right here, because I'd have to know what kappa lambda and rho were as functions of s to be able to do it. So I'm just going to say whatever this integral is, it's still there. So this is equal to still minus the integral from 0 to s of kappa lambda rho ds prime. Questions, comments, observations? You all buying what I'm selling here in the math department here? Okay, so on the left we're going to get natural log I lambda. Well, what are we going to do? We're going to get natural upside down. Okay, natural log I lambda minus natural log I lambda naught. Okay, minus natural log I lambda naught equals still integral from minus integral from 0 to s of kappa lambda rho ds prime. How can I rewrite natural log of I lambda minus natural difference is equal to the log of the ratio. So this is natural logarithm of I lambda over I lambda naught is equal to, it's still that integral, minus the integral from 0 to s, capital lambda rho ds prime. How do I undo that logarithm? How do I undo the natural logarithm? 2, 4, 6, 8, time to... That doesn't rhyme here. 2, 4, 6, 8, time to raise both sides, time to raise e to the power of both sides. Okay, it's going to flow better if we say 2, 4, 6, 8, time to exponentiate. That works better, right? 2, 4, 6, 8, time to exponentiate. And so, take e to the power of both sides. 2, 4, 6. No, let's see. These are going to be fun rides. We'll take e to the power of both sides. There, kind of make that work too. All right. So therefore, we're going to get that I lambda over I lambda naught is equal to e to the power of minus the integral from 0 to s of capital lambda rho ds prime. Or, in other words, what we can say is that I lambda as a function of s is I lambda naught times e to the minus that integral, 0 to s of capital lambda rho ds prime. Voila. Bought what I've sold. Now, it could so happen, it wouldn't be shocking if the conditions of the surrounding material through which the beam is traveling are uniform, then kappa, lambda, and rho could be constant with position. In which case, we could just pull them out of that integral. For kappa lambda equals constant, and rho equals constant, or if by some miracle kappa lambda and rho are varying but inversely in one another so that the combination stayed constant, but that'd be kind of unlikely. If they're both constant, we'll then have that this is just I lambda is equal to I lambda naught e to the minus kappa lambda rho s, because when we do that integral right there, kappa lambda and rho are constants, you can pull it out, and the integral from 0 to s of ds prime is just s. And so it just becomes e to the minus kappa lambda rho s. So that's an important special case, which wouldn't be all that rare. It could very well be that you're interested in radiation traveling through a material whose properties are constant along the beam. So what's that look like? What is this? It's x d k. Yes, yeah, very good, right? So, yeah, there we go. Yes, yes. It's an exponential decay with distance along the beam. Exponential decay of I lambda with distance along the beam. So in other words, it looks something like that, right? It looks something like that. It's just exponentially decaying. Strictly speaking, does it ever go to 0? No, it's an exponential decay. So after infinite distance, the intensity is finally 0. Now, there's only a finite number of photons in the beam, so in practice, you're finally going to eat the last photon. But in principle, the math says it takes forever. Since it's actual photons, it will never actually take forever because you would finally get down to the last photon. But the same is true with exponential decay of the sample, right? Strictly, if you look at the math, it says it takes an infinite amount of time for all the atoms to decay. But that's assuming there's an infinite number of atoms there. If there's a finite number of atoms, you eventually get to the point where there's only one left, and that's going to decay, and we're done. So, there's an E folding distance here. In other words, the distance over which the intensity falls to 1 over E of what it initially was, the E folding distance. Over what distance does the beam fall to a value of 1 over E of its initial value? In other words, for what value of S is the beam down to 1 over E of what it started with at S equals 0? And like we were talking about last time, it doesn't matter where you start. Over that same distance, it falls by a factor of 1 over E. Just like with the temperature scale height, if you have an exponential decay of temperature, doesn't matter where you start, scale height later, you're down by a factor of 1 over E. This is analogous. 1 E folding distance later, we're down by a factor of 1 over E. What value of S makes this I naught E to the minus 1?
1 over
Kappa rho, 1 over kappa rho. The E folding distance is 1 over kappa lambda rho. 1 over kappa lambda rho. Which is also the photon mean-free path the average distance a photon travels before getting eaten. In this case, it's going to be scattered out of the beam or absorbed out of the beam. It's also the photon mean-free path. That'll be the average distance a photon travels before being scattered or absorbed. And again, it doesn't matter where you start. All that matters is if the photon has survived to that point, all the photons that have survived to a given location along the beam, 1 over kappa lambda rho is the average distance that any given photon will travel before it gets eliminated from the beam. Average distance a photon travels from any given starting point before being absorbed or scattered out of the beam. And again, this is like exponential decay, right? In other words, atoms don't become due to decay. It's not true that, wow, the longer an atom in a radioactive sample has lived, the more likely it is to decay soon. It's not like that at all. No matter what time it is, any given atom has a constant probability of decay per second, no matter how long it's already been there. It doesn't become more and more likely to decay. And similarly here, photons don't get more and more likely to be absorbed as they travel. There's always the same probability of being absorbed per unit length, but the further you go through the beam, the more photons will end up being absorbed. But it's always true. It's always the same distance if the properties are constant of the material doing the absorbing, always the same distance such that you're down to 1 over E, or you could also make it always the same distance over which half the photons were absorbed if you wanted to make it that, which would have a simple relation to this E folding distance. So I have made an assumption, not assumption, I made an assertion, which I did not prove. I said that's the photon mean free path. Please consider looking at my notes for the derivation. So I do derive that that is in fact the photon mean free path in my notes, and if you're sufficiently interested, you can see the derivation there. But I don't want to spend class on it. But it is in fact true that 1 over capital lambda rho is the photon mean free path. Take my word for it, or see the proof. It's not too bad, but it would take a while, so I don't want to do that. So for a photon, we can write that the MFP, maximum fluoride protection, I was asked that yesterday in office hours. What was that about? What's this MFP stuff? And so I showed an old commercial for fluoride toothpaste from the 80s where they do talk about it's a mom and her daughter, and the daughter's playing the mommy and telling like her mom / daughter, you should brush your teeth with Colgate with maximum fluoride protection, you know. And it had maximum fluoride protection. And I put registered trademark, although, in the commercial it went like this. Oops, maximum fluoride protection. So it did the little circle R underneath it. Okay, whatever. Anyway, the mean free path, L, is 1 over capital lambda rho, 1 over capital lambda rho, and from our earlier arguments, we can also call that 1 over n sigma lambda if we like, where n would be the number density of the photons. And sigma lambda would be the interaction cross-section as a function of wavelength for the photons. So sigma lambda is the photon absorption cross-section. Can I erase this board over here? Nobody's stopping me. It goes. Okay, let's get deep and profound here, because we're going to talk about optical depth. Optical depth. We use the symbol tau lambda for that. Tau sub lambda is what we use for the optical depth as a function of wavelength. Here's the definition of it. D tau lambda, a little change in the optical depth along the beam, by definition is minus kappa lambda rho ds. In other words, it's everything except the I lambda on the right-hand side of our transfer equation. The di lambda equals minus kappa lambda rho I lambda ds. This is everything else. Here's my beam, S off in this direction, and what we're saying here is that the minus sign says that tau lambda and S increase in opposite directions. And so what we typically will think of as is here is the observation point. And actually, yeah, how do I want to do this? I think, yeah. So I actually want to go in the other direction the way I've drawn this. So here's the observation point. What's that supposed to be? It's an eye. Yeah, this is a cross section of an eye, right? It's not a great one. It's eyeball, right? So eye. That's what that is, okay? And so we'll have S increasing, S is, no. Now all of a sudden I've got myself so far. Don't draw anything yet! I gotta get myself happy. No, right? It's, yeah. So, okay. This is, I was right the first time. That's S equals 0. So here's source located here. Right? So maybe it's your phone flashlight. There's a source of light, and you're looking at it through some hazy stuff, and you want to know how much light actually manages to make it to you through the haze. So S equals 0 is where the source is. So S is increasing in that direction. And the optical depth is 0 where you are doing the observing, and increases in the other direction. That's our convention. Tau lambda increases opposite to the direction of the beam. So tau lambda increases away from the observation point. At tau lambda is equal to 0. Does that make sense? That's how we do this. So the further, if I'm holding my flashlight up and it's foggy, hazy in here, the further away I am from you, the greater is my optical depth away from you. Because we want to capture the idea that the further away something is, the harder it is to see. Because more and more light has been absorbed on the way. So now, let's say here's the top of the stellar atmosphere. And by the way, everything we say here can be applied to Earth's atmosphere as well. So this could all be, this is more general than just stars for sure. And sometimes we talk about, like if we're on Earth looking at stars, well, then we're looking at the beam is moving towards us from outer space. Here we're going to be talking about, here's another layer with it, some layer below the surface of the star sending light outwards, and that light reaches the surface and escapes into outer space. And if we're looking at the star, if we're imagining looking at the star, this is a matter of then like, how much of the light can I see from each layer as I look deeper and deeper into the star? That's kind of the general idea here. So here's the top of the stellar atmosphere. Is that really a thing? Strictly speaking, no, because stars are big fuzzy gas balls, and so they don't have sharp edges like that. And so you just have to define some level where you're satisfied that, yeah, it's thin enough there that we're going to just pretend that that's where the star ends. But there's always going to be some ambiguity in what you mean by that. So let's ignore that ambiguity. There's the top of the stellar atmosphere weak. Okay? And so we're going to call that tau lambda is equal to 0, because in this case, we're going to assume once it escaped from the star, the photons are free to travel. There's no absorption anymore, there's nothing up there. And so tau lambda is 0 there, it's 0 up here too, it's 0 up there too, because there's no absorption. And so tau lambda stays constant at 0 above the atmosphere, because d tau lambda above the atmosphere is 0 because there's nothing there. And so d tau lambda is 0. It's staying constant at 0 above the top of the atmosphere. Here's some point within the star. Here's a point below the surface. And we want to know how much light from that point gets out of the star, leaves the surface. How many, in a sense, like what fraction of the photons, if you will, that are coming from that point actually make it to the surface without getting absorbed or scattered first. And so what we'll do is we'll say, okay, let's call the z-axis the direction perpendicular to the surface. Here's the z-axis. And we might be looking at an angle to the surface at an angle theta to the vertical. And if you've ever been exposed to me talking about limb darkening, this is directly involved in that sort of thing, when you're not looking straight down into the surface, but at an angle to the surface. That's what you're doing if you look towards the limb of the stellar disk. If you're looking away from the direction to the center, that's what's applying here. So we're looking at an angle theta away from the perpendicular to the surface. Let's use what we know here to say something intelligent about all this. And I should point out here, by the way, that here we're going to say that now this is increasing S. And so I've changed my perspective a bit from before for my doing this particular piece. We've got some latitude. S is always the direction of the photons traveling along the beam. And so now, so now I'm thinking that picture I drew before, well, not wrong. I had, let's see, I was doing that before, right? I had S over there on the left. Yeah, okay. I'm confusing myself. Stop confusing me. Okay. All right. So yeah, here's increasing S. Okay. So this will be S is equal to 0. And tau lambda is greater than 0. This is at some optical depth below the surface as seen by somebody looking along that direction. So somebody's looking along that direction. That's too high up there. That's an eye looking in that direction. How much light do I get from that point? How much light do I get from that far below the surface? How many of the photons make it to me, so to speak? So S is 0, tau lambda is greater than 0 down there. Tau lambda is equal to 0 up here at the top, at the point where the photons are free to fly. So the change in tau lambda between that point and the surface delta tau lambda will be equal to the integral from tau lambda to 0 d tau lambda prime equals, well, if I do this integral, it's tau lambda prime, a value between 0 and tau lambda, so that'll be 0 minus tau lambda is equal to minus the integral from 0 to s, capital lambda rho ds prime. So I'm integrating from my source point down here at s equals 0 up to the surface. So s, this whole distance here, that whole distance that the beam has traveled to get to the surface, that's s. So in other words, tau lambda is equal to the integral from 0 to s of capital lambda rho ds prime. And that gets a box. So the optical depth at any point below the surface is the integral along the path from that point to the surface in the direction that we're interested in of capital lambda rho ds prime along the beam there. So it's time for a break, so we'll continue after the break. I can't wait. Continuing the sentence I was about to write here, which corresponds to our picture here. We always said s equals 0 at the starting point. I mean, we don't have to, but this is just a good habit to get into. We always set s equals 0 at the starting point, the place where we're interested in knowing how many photons, so to speak, we're getting. Always set s equals 0 at the starting point, or really, how much of the specific intensity at that point we're getting. The deeper in the atmosphere we start, the larger is the final value of s, and thus the optical depth increases as we would expect. The deeper in the atmosphere we start, the larger is the final value of s. The total distance along the beam, in other words. And thus, the optical depth increases as we would expect. The deeper into the star you're looking, the greater is the optical depth of the layer to which you're looking. So if you imagine Somebody sinking deeper and deeper into the star's atmosphere in an amazing spacesuit that keeps them from being vaporized. Further down they go, the greater is the optical depth at which they lie. And we're receiving photons from the sun's a gas ball, no sharply defined surface, no edge. So if you look into a star, you're getting light from many, many layers, so to speak, just light. But the further down you go, the less light from the layer in question is reaching you. And as we'll see, not today, but as we'll see, you can talk about kind of how far into the star can you see, what do we mean by that, and so forth. The reason why the sun appears to have a sharp edge is that the photosphere, the layer from which we're receiving almost all of the photons, the layer from which photons last scatter on their way out of the sun, is about 400 kilometers thick. That's where the optical depth is equal to 2/3, as we'll see. But 400 kilometers is a very tiny fraction of the sun's diameter. And in fact, the angular resolution of a telescope on Earth's surface at the sun's distance is about like 700 kilometers. That's the smallest things you can see on the sun, is about 700 kilometers. So that surface layer, that fuzzy surface layer, is too thin to even resolve. If you draw, I'm going to draw a picture of the sun. That chalk line I drew is much thicker compared to that circle that I just drew than the photosphere of the sun is compared to the actual sun. So it gives the illusion of having a nice sharply defined surface, even though it doesn't. It's a fuzzball, and if you could get really close to the sun, you would see that it's a fuzzball, but we're too far away to see that. That's what it comes down to. So here's another thing to note here. Since L lambda, remember, is 1 over kappa lambda rho. What's L lambda represent? It's the photons. Yep, mean free path, right? Photons, mean free path, maximum floor, no, mean free path. Ding. I should be like, every time I say mean free path, I should except I don't have lovely white teeth, but I should smile. A little glint happens on my teeth too. Maximum floor. Anyway, since L lambda is 1 over kappa lambda rho, notice that tau lambda is equal to the integral from 0 to s of, well, remember, it's kappa lambda rho ds prime. It's minus the integral from s to 0, so I flip the limits to 0 to s equals the integral from 0 to s of ds prime over L lambda, because kappa lambda rho is 1 over L lambda. And if you think about what that means, well, ds prime divided by L lambda is the fraction of a mean free path traversed in that little distance ds prime. Right? It's the fraction of a mean free path. Little distance ds prime over the mean free path is the fraction of the mean free path traversed in ds prime. So we're adding up all those little fractions of mean free paths to get, in the end, the total number of mean free paths between the source of light and the observer. This is, the optical depth can be interpreted as being the total number of mean free paths, MFPs, between the source and the observer. So just to be sure you're paying attention / getting this, if I'm observing something at an optical depth of 1 away from me, how many mean free paths are there between me and that something? Yeah, okay. So suppose wherever you are, we could just use, okay, you're looking at me, I am at an optical depth of 1 at your location. Okay? So how many photon mean free paths are between me and you?
1 over.
Now you're overcomplicating it. Yeah, the optical depth is the number of photon mean free paths. So if I'm, it's what I was saying, right? Just be sure, right? Just be sure you're clicking here, right? So if I'm at an optical depth of 1 away from you, that means that there's 1 photon mean free path between me and you, which means that you're at the distance away from me that corresponds to the average distance a photon travels before scattering or being absorbed. Now, does that mean every photon travels that distance? Certainly not. Some of them scatter or absorb before then. Some of them scatter or absorb after that. So not all those photons that are sending your way reach you. About what fraction do reach you? What is I lambda? If I lambda naught, here I'm going to turn on my flashlight just to be. Did I restart that? I don't remember. Did I? I better check. I think I did. Yeah, I think so.
Yeah.
I think I did.
The light's blinking.
Is it? Yeah, that's a good sign. And yeah, okay, good. You're seeing me then. Good. Okay. So it's like, ah! Right? Yeah. Sorry, Willow. Sorry, Kayla. Sorry, Anushka. Okay. Here we go. Right? Yeah. Okay. Now, you're actually much less than 1 mean free path away. In this case, the air is transparent in here. But if it were easy in here, such that I was 1 optical depth 1 away from you, what fraction of the intensity is reaching you? Remember that kappa lambda rho was the E-folding distance as well. The photon mean free path is also the E-folding distance. So I lambda is what fraction of I lambda naught at your location in this hypothetical scenario where your tau lambda equals 1 away from you for whatever wavelength we're interested in. 1 over E, yeah, 1 over E, right? 1 over E. So 1 over E is the fraction of the photons that are reaching you. 1 over E, if you make a rough estimate, it's about 1/3, right? 1 over 2.7, whatever the hell it is, 2.78. So about 1/3 of the photons are reaching you, right? So 2/3 of the photons are getting eliminated before traveling the mean free path. Is that a contradiction? No, because so only only roughly 1/3 of the photons actually make it to the mean free path. But remember, the mean free path calculation would also include photons that travel further than that. And so some of those photons, just by coincidence, are going to travel many, many mean free paths before they finally get eliminated. And that skews the average to be what it is, you know. So you have roughly 2/3 of the photons are scattered before that. That other third includes some photons that travel way past the mean free path distance. And when you put them all together, it averages out to the mean free path. But keep that in mind that most of the photons actually interact before one mean free path. What's that?
Is it on?
It's still on. Oh, it is, yes. You can still see it a little bit. Yes, thank you. Right. There we go. Gone. All right, happiness. I'm not blind when I'm doing that. Okay. Okay. Right. in one of them, so again, later we're going to talk about the sense in which we can see to an optical depth of 2/3. And it's not to be taken literally, but we're going to find that under certain approximations, right, the temperature in the atmosphere is increasing as you go lower down. It gets hotter as you go further into a star. So you can talk about the temperatures of different layers. And remember, we can talk about TEF, the effective temperature. Well, the radiation you see is coming from layers at lots and lots of different temperatures, a spread of temperatures. And remember, the flux that you see by definition is sigma TEF to the 4th. But it's a blend of layers of many different temperatures. And it turns out under certain assumptions that the actual temperature of the layer at an optical depth of 2/3 is equal to TEF. T equals TEF at an optical depth of 2/3 under certain assumptions. And even if those assumptions are not quite true, it's still going to be roughly true that T is equal to TEF. The actual temperature of the layer is equal to TEF around an optical depth of 2/3. So in other words, the light coming from the star in terms of the flux we're receiving kind of looks like the light that would be coming from the layer at an optical depth of 2/3. And so we summarize that by saying we see to an optical depth of 2/3, which again is sloppy speak because we're seeing light from layers above that, we're seeing light from layers below that, but we're seeing less and less light from layers more and more below that. And so in a sort of average, we can say we see to an optical depth of 2/3. If I'm in a fog, again, we can describe it in terms of optical depth. If I'm at tau equals 1 away from you, about 1/3, 1 over E of the light reflecting off me is actually reaching your eyes, and so I'm starting to look kind of fuzzy, right? A fog looks hazy because light that normally would have gone straight to you, here's a photon that was going to go straight to Kathleen, oh, but instead it hit this fog particle over here, and then it went to her, or any one of you. So you're getting all this light from fog particles that are photons that would have missed you, but then they get scattered in your direction. So you see this haze everywhere from photons that are being scattered in your direction, and meanwhile things you're looking at get harder and harder to see because the photons which would have reached you directly, making a nice clear image, are fading out because more and more of them are not making it to you. They're getting scattered off in some random direction instead of making it to you. At an optical depth of 1, you're only seeing about 1/3 of the photons reflecting off me. I'm starting to look hazy. At an optical depth of 2, about what fraction of the photons are you seeing from me? So if 1 over E is what you see at an optical depth of 1, if I add an additional delta tau equals 1, right? From tau equals 2 to tau equals 1, 1/3 of the photons make it there. And then from tau equals 1 to tau equals 0 at your location, 1/3 of those photons make it there. If we're really exactly clear, I'll be more exact. 1 over E make it from tau equals 2 to tau equals 1, and 1 over E of those make it from tau equals 1 to tau equals 0. Now it's math at tau equals 0. What fraction of the photons reflecting from me are making it to you if I'm at an optical depth of 2?
1 over 2 E.
Not 1 over 2E, 1 over
E squared.
E squared, right? 1 over E times 1 over E, right? Which, if it was 1/3, it'd be 1/9. I'm guessing 1 over E squared is closer to 1/8 or something like that, because 1 over 2. If I'm at an optical depth of 3 away from you, it's 1 over E cubed, right? Et cetera, et cetera. Getting harder and harder to see as you go further and further away. And so by the time you get to an optical depth of 3, not a lot of the light is making it there. So in the real fog, if somebody's walking away from your real fog, right, they kind of disappear at an optical depth of something like 3 or 4 or something like that. It's the point where you just can't see them anymore. And they're just gradually fading, but exponentially so, as they get further and further away from you. And think of that in terms of the star as well. We look into the star, and as you go deeper and deeper into the star, you're getting less and less light from layers deeper and deeper in, as though things are disappearing into a fog, so to speak. In one of the homework problems, you're asked, how far could you see in Earth's atmosphere if it had the same opacity as the solar photosphere does? And the answer that you can give is basically consider it to be just calculate what distance corresponds to the photon mean free path. Because that would be putting something at an optical depth of 1. And so you could say, okay, you can see about 1 photon mean free path. Not literally, because if I'm 1 photon mean free path from you, you're seeing about 1/3 of my photons. You're definitely seeing me. Cool. If I'm optical depth 2 away from you, you're still seeing me, but it's getting kind of hazy. In other words, when they talk about visibility, right, on the weather, right, you can't literally say, I can see this far and no further in the fog. You have to make some cutoff to define what you mean by how far you can see through the fog. For that problem, I'm fine if you say, just calculate what the photon mean free path is, and that's how far you can see. And what you should find is that it's not that far. If the Earth's atmosphere was as opaque as the sun's atmosphere per kilogram, we'd be in a pea soup fog, so to speak. Earth's atmosphere would be pretty opaque in that case. But in the sun, you can see a lot further. Why? Because the sun's atmosphere is much less dense. The photosphere is much less dense than Earth's atmosphere is. So that the actual distance you can see is much larger. But if you look at the per kilogram opacity of the solar atmosphere and apply it to something as dense as Earth's atmosphere, about 1.2 kilograms per cubic meter, then no, you couldn't see that far, which is an interesting factor I want you to see by working out that problem. By the way, too, just as an aside, so yeah, the density of air is roughly 1 kilogram per cubic meter, right? Kilogram per cubic meter, okay? What would be a mass of water in a cubic meter? What's the mass of water in a cubic centimeter, roughly speaking? 1 gram, right? How many cubic centimeters in a cubic meter? So a centimeter, how many centimeters are a meter? 100. So a cubic meter is 100 centimeters by 100 centimeters by 100 centimeters. How many cubic centimeters? 100 times 100 times 100. 10 to the 6th power is a million. It's a million. So a cubic meter of water, be thinking of doing these kinds of calculations in your head. They're good things to get in feel of it. So a cubic meter of water is 1,000,000 grams. How many kilograms? 1,000 kilograms, right? Because a kilogram is 1,000 grams. So a cubic meter of water has a mass of 1,000 kilograms, which is what we call a metric ton. So a cubic meter of water has a mass of a metric ton. How many pounds is that roughly? Because Murray, right? How many pounds is that?
Around 2,000.
Yeah, around 2,000, because there's 2.2, a kilogram weighs about 2.2 pounds, so it's like 2,200 pounds. An English ton is 2,000 pounds, so a metric ton and an English ton are fairly comparable. So a cubic meter of water weighs about a ton, right, is the idea there. A cubic meter of air, instead of 1,000 kilograms, is about 1 kilogram. So first of all, on some level, that's kind of surprising to me when I think about it, right? Because if I go grab myself a kilogram, I'm going to grab myself a kilogram. You know, if there's one thing I want right now in my life, it's a kilogram. And it'll work better if I use the right key, it turns out. I want me a nice kilogram. I hope I got a kilogram in here. It'd be tragic if I don't have a kilogram here. Please have a kilogram. Yeah, here we go. Here's a kilogram right here. Here's a kilogram. It's actually, I mean, I'm used to it now. It's actually a little surprising to me on some level that a cubic meter of air has that much mass in it. A kilogram. A cubic meter of air is a mass of a kilogram. So it's about 1,000th as dense as like water is, right? So what's the average distance between air molecules compared to liquid water molecules? if the volume, if it's 1,000 times less dense, then the same amount of mass is spread, if you turn it into water, right? Turn water into, well, okay, roughly. Water is roughly. I'm going to not worry about how much the mass of each molecule is. But anyway, if you took a substance and you went from, when it's liquid, 1,000 kilograms per cubic meter, gasify it and get it to a density of 1 kilogram per cubic meter, right? It's 1,000th the density. So the volume will have increased by a factor of 1,000 to spread it out to 1,000th the density. So what happens to the average distance between the particles to make the density go down by a factor of 1,000? How much further apart do they have to be? 10 times further apart, because 10 times 10 times 10 is 1,000. If they're 10 times further apart, the volume will have increased by a factor of 1,000. So the average distance between air molecules is about, who is it? I mean, that guy, who is this? Oh, Hilton again. Shut up, Hilton. This is fake Hilton call it. It doesn't do any good to call it spam. I can mark it as spam, but they just, amazingly, the number changes every time. It's not that Hilton, trust me. So in the air, the molecules are about 1,000 times further apart than in solids and liquids, roughly speaking. So the mean free path between collisions is about 10 times further in the air than it is in like water and stuff like that. Just roughly speaking, right? So good to think of things like that. Okay. Questions, comments, observations? Okay. So continuing on here with this stuff. Note that the optical depth corresponding to a given geometrical depth, by that I mean the vertical distance down. So here's the geometrical depth of that point. It's like if you're in a swimming pool, the geometrical depth is how far below the surface in our star. The geometrical depth is how far below the surface if you go straight down. The geometrical depth is that distance. The distance, if I put some angle theta to the vertical, is bigger than that. I'm looking through a longer path length. And so the optical depth corresponding to a given geometrical depth depends on the value of theta. Optical depth corresponding to a given geometrical depth depends on the value of theta in the figure. You're looking through a longer length of atmosphere, if you're looking at angle theta away from the vertical. For a plane parallel atmosphere, in other words, we ignore the fact that the star is really spherical. If we're looking at some small region, you can just be a flat star, so to speak, and just consider everything to be flat. Just like with Earth's atmosphere. Surely the atmosphere is really spherical because Earth is, but where you are, it's not a bad approximation to consider just planar. The top of the atmosphere is a straight line like I drew there as an approximation to really it's just part of the giant arc that goes around the entire star. So by a plane parallel atmosphere, we're ignoring the fact that it's really a sphere. For a plane parallel atmosphere, which is often a first approximation made in modeling stellar atmosphere. For a plane parallel atmosphere, tau lambda is integral from 0 to s of kappa lambda rho ds prime. Right before I had minus the integral from s to 0 capital lambda rho ds prime, but that's the same thing as integral from 0 to s of capital lambda rho ds prime. Well, if we call the geometrical depth h, so in other words, this point is at z equals 0, and the top of the atmosphere is at z equals h. The integral from 0 to s of capital lambda rho ds prime, well, that'll be the integral from 0 to h of capital lambda rho times dz over the cosine of theta. Right? In other words, for any little piece of the path here, here's ds, there's theta, there's dz, right? Then dz is ds over the cosine of theta, right? In other words, you know, SOHCAHTOA, right? Cosine opposite over hypotenuse. Well, 1 over cosine is hypotenuse over adjacent over hypotenuse versus cosine. Cosine is adjacent over hypotenuse, so hypotenuse is adjacent over cosine, and that's what I'm doing there. ds is dz divided by the cosine of theta in this triangle. Is that making sense or not? So for a little piece of path here, there's the little distance dz vertically, there's the little distance ds along the path at angle theta. Oh no, can you see that at all? So this one, this is a little piece ds, that's a little piece dz. And so I just compacted them into this little triangle right here. There's a right triangle, ds along the path of the ray, dz is the vertical distance that has been traveled, just that vertical component, at angle theta away from the vertical, right? So cos theta is equal to dz divided by ds. So ds is dz over the cosine of theta in the integral there. Is that making sense or not making sense? I feel like you're not like, yeah, it makes perfect sense. What's confusing you, sir? Anything? The idea here, right? It's just that I'm moving in an angle here. So as I move along, I'm moving more than the vertical distance I'm traveling here. The dolphins are straight up and down distance because I'm traveling on a slant. So a little path length ds, a little path length dz. This is a little right triangle. Cosine theta is ds over dz. This is a magnified version of that little piece of path right there. I'm considering the vertical component of it and the component along the direction photons are actually traveling, that angle theta away from the vertical. So therefore, ds is, I could call it ds prime if I want to. ds prime is dz divided by the cosine of theta. Can somebody tell me what is 1 over the cosine of theta when we just give it its own name? Yes, that's the sec of theta equals dz sec theta. Sec, and ye shall find it's constant. Theta is constant in this picture, so you can pull it out. So we get the secant of theta times the integral from 0 to h of capital lambda rho dz. But that would be the optical depth looking straight down. If we look straight down, ds and dz are the same thing. So the vertical optical depth is the optical depth you see looking straight down into the surface instead of some angle to the normal. So we call this tau lambda sub v secant of theta. say that, in other words, tau lambda along our actual ray is tau lambda v sec theta, where tau lambda v is the vertical optical depth. In other words, optical depth looking straight down into the star, or straight down into the atmosphere. I hope I was allowed to erase that.
Oh, no, oh, just, oh.
So I will mention too here that when we're doing observational astronomy, we turn this around. In other words, in observational astronomy, we are within the atmosphere looking at stars that are well above the atmosphere, so to speak. We flip the whole thing around and we say, okay, how much of the star's light reaches us? And the answer is, the lower the star is in the sky, the less light reaches us because the light is moving on a slant, traveling through a longer length of atmosphere. And so we talk about what we call the air mass, capital X, and if we make the approximation of a plane parallel atmosphere, capital X is the secant of theta, or in fact we say it's the, oh, that'll get confused. It's the secant of theta, where theta is the angle the star makes with the zenith, the straight overhead direction. And so, why are you looking at me like that? What did I do?
Does that say AIN?
Well, yes, it does, but it's supposed to say air.
I'm sorry.
Yes. That ain't mass.
It just appeared on the board.
Yeah.
I was like, what is that?
Sorry, yeah. That's the air mass we call it.
Thank you.
X equals the secant of theta. So if theta is equal to 0, what is x equal to? What's the secant of 0? What's the 1 over the cosine of 0? So what's the secant of 0? 1. X is equal to 1. So in other words, straight overhead to say the air mass is 1. And at any other angle theta, it's the secant of theta. Now, just to be confusing, what we actually say is that the angle from the straight overhead direction, we actually call that z the zenith angle, but then that would get confusing because I call z the z-axis here. But I'll just say, usually we say x is the secant of z the zenith angle, but it's the same idea here, okay? And so stars look dimmer when they are not straight overhead. How much dimmer? To a good approximation, the answer is they're dimmed by a factor of secant theta, secant of the zenith angle. And the plane parallel approximation starts to break down when theta is, when z, that zenith angle is about 60 degrees or so. Or in other words, when the star is about 30 degrees above the horizon, you would start to notice the fact that the atmosphere is actually curved and not flat. Because, right, for a curved atmosphere, it's the extra length you're looking through is a little bit less than that factor of secant theta, is what it comes down to. And for Earth's atmosphere, for a planet of our size, if the zenith angle gets to more than about 60 degrees, or the angle above the horizon is less than about 30 degrees, you need to make a correction for the fact that the Earth's atmosphere is actually curved. But, in other words, the stuff we're talking about here loops back to observing stars through Earth's atmosphere. It's the same physics, is what it comes down to. And so, you know, why does the sun look dimmer when it's lower in the sky? Because of frickin' this, is what it comes down to. And so, if we really had a plane parallel atmosphere, the sun would not be visible on the horizon because you'd look through an infinite length of atmosphere. But of course, that's not really true. And also, if there's clouds there, it's messing everything up and so forth. But this is the basic physics of that, is what it comes down to. Okay? Questions, comments, observations? Glorious. Yeah, I think it's glorious. Glorious. Glorious gloriosity. So we'll come back to that idea of the vertical optical depth when we go into stellar atmospheres in more depth. Yeah. And notice, by the way, right, what we're doing right now. So first, I personally think this is fascinating in its own right. It has applications to Earth's atmosphere, to stellar atmospheres, to planetary atmospheres. At the same time, right, what we're doing is laying the groundwork for actually understanding stars in general, right? It's kind of like, I feel like, you know, nobody would go into astrophysics because they want to understand optical depth, but you need to understand optical depth in order to understand many phenomena in astrophysics, right? I don't think anybody goes into physics because they want to study blocks sliding down planes, but learning about blocks sliding down planes helps you learn to study more interesting systems than that. And so what we're doing is laying the foundation to study cool stuff later, is what it comes down to. I think this is cool in and of its own right, but we're laying the groundwork for studying cool stuff later. We're going to apply this to actual stars and so on and so forth. So, sources of opacity in a stellar atmosphere. What's making it hard for photons to get through? Sources of opacity in a stellar atmosphere. And because we're just getting to this now, I guess I'll say, this is on the study guide. I guess I'll take it off because we'll have gotten to it by the time of the exam because we'll finish this on Tuesday, but that's not fair to say. And so know this by the exam. So I'll take this particular stuff. So we are now done with everything that's on the exam. What I'm doing now won't be on the exam. Okay, so where's the tears? Okay, very convincing, yes. Okay, so you got number one, bound absorption. Bound absorption. The bound refers to, is the electron attached to an atom or not? If it is, it's bound. If it ain't, it's free. So bound absorption means the photon starts attached to an atom, the photon ends attached to an atom. In other words, this is, photon comes in and say, kicks an electron from n equals 2 to n equals 4 in the hydrogen atom. The making absorption lines is bound absorption. That's that process. So bound absorption occurs when an electron bound to an atom absorbs a photon and jumps to a higher energy level. Electron bound to an atom absorbs a photon and jumps to a higher energy level. In other words, this is the process that makes absorption lines. period. In other words, this is the process that makes absorption lines. And you could have the electron jump right back down to the level it jumped up from, in which case, in a sense, you just scattered the photon. You kind of recreated it and sent it off in another direction. But it could also jump from n equals 2 to n equals 5, and then to n equals 3, and then to n equals 2. And then you would take, essentially, you start with one photon and turn it into two photons that both have lower energies. So this process can both essentially scatter photons without really changing their wavelength, if you want to consider the emitted photon to be the same photon as the one that was absorbed. How many angels can dance on the head of a pin, right? You know, it's like, what, have you heard that before? How many angels can dance on the head of a pin? Yeah, that's like a philosophical question about, like, well, do angels have volume? And blah, 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 right? It's not defined physically, but in any case, that's kind of a generic way of saying, like, you know, a photon gets absorbed and disappears. Then the atom jumps back down to the same level and re-emits a photon with essentially the same energy. Is that the same photon having been scattered, or is it a new photon? Whatever, right? Ship of Theseus, if you've heard of the ship of Theseus before, right? This can either kind of redirect photons, or it can take one photon and redistribute its energy in a bunch of new photons if it doesn't jump all the way back down to the same level it started from. Two, bound-free absorption, or photoionization. Photoionization. That's a $2 word right there. Say that to your parents and make them be impressed with how smart you are, how good it is that they're spending money on educating you. Hey, mom and dad, you want to talk about photoionization, right? You know, some good word there. Bound-free absorption. Well, what's happening here? The electron starts attached, it ends no longer attached, it's free. In other words, this is when a photon comes in with enough energy to ionize an atom, is what it comes down to. It occurs when a photon has enough energy to ionize an atom. And I think just for, I still won't put it on the test, but rather than say a little bit more specific about this, I'm just going to list the other processes, and then we'll come back and say a little bit more details about how they're described mathematically. And we say photoionization because photons aren't the only way to ionize an atom. It could also have a violent collision with another atom or with an electron and strip off an atom and ionize it. So photoionization means ionization by photon. And then we've got free absorption. Free absorption. And now I just put, won't be an earworm in your ears probably, but it is in mine now because I hope y'all, please tell me you know who Sting is, like from the Police, right? As the song goes, free, free, set them free. Oh, oh, free, free, set them free. So, oh, okay, fine. So that's in my head now. Thanks, me. Free, free. I hope it's not in your head. Y'all don't know that song at all, or is it not? Yeah. Didn't think so. It's a good song. But anyway, free, free absorption is from the classic album, Dream of the Blue Turtles. Free, free absorption occurs when electrons are scattered by free electrons rather than absorbed. When electrons, E minus, are scattered by free electrons rather, oh no, that's a lot. What am I talking about? The next, doesn't make any sense. It's rather than absorbed for free absorption. What the hell, me? Occurs when a free electron near an ion absorbs a photon and thus picks up speed. Occurs when a free electron near an ion absorbs a photon and thus picks up speed. In other words, its KE increases. It uses the photon's energy to do that. And the ion is needed so that both momentum and energy can be conserved. Because in the homework, you're going to joyfully show that an electron by itself can't absorb a photon because you can't conserve both relativistic momentum and energy if you try to do that. So a free electron can only redirect a photon. It can scatter it. It can't eat it. It cannot absorb it. So you need an ion nearby to take up momentum, so to speak, so that both energy and momentum are conserved. So this might be a new concept to you. If we make a kind of quasi-Feynman diagram here, there's the electron coming in, and here comes a photon, and here's an ion nearby. There's a photon coming in. In other words, we've talked before about there's an electron, and it's in a bound state. Photon comes in, kicks it up to a higher energy bound state. It can also happen with free states. So if you've ionized the atom and the electron is no longer in a bound state, see if you know this, is the energy quantized for an electron that isn't bound to an atom? It is not. The electron, just like classically, can have any energy that you like if it's not attached. And that's because you know in quantum mechanics, it's boundary conditions that cause quantization. If it's free, it doesn't have boundary conditions that it needs to satisfy like it would if it were bound. The wave function doesn't have those boundary conditions. And so here, there's a continuum of photon energies that can do this. It's not discrete anymore. So this is a source of continuum absorption at over a whole continuous range of wavelengths, not particular wavelengths like mixed spectral ones. But this can happen. An electron that's near an ion can be kicked to a higher kinetic energy, unbound orbit, so to speak, although really it's a quantum mechanical process that's describing this. And so that's called free absorption. And it's time to go. I've given you some bonus education here. So we haven't talked about electron scattering. I'll try to do that next. And put in some preparation. All right. See you next time. That would be unfortunate. You want camera too? Yeah. It's weird. Dr. Harmon's last words were, see you next time. And then Right.